Hi, my name is Matheus Macedo. I will be presenting the paper Machine Learning Predictions of the Turbulent Flow in the Square-Duct employing a transport equation for the Reynolds stress tensor. This was co-authored by Roney, Thompson and Matheus Altomare Cruz. We are all members of the Department of Mechanical Engineering in the Federal University of Rio de Janeiro. At first I'll make a brief introduction of the subject, then I'll make a quick review of the literature concerning machine learning assisted turbulence. Then I will explain the data-driven turbulence model based on the Reynolds stress transfer equation that we developed. Then I will present the application of this model in the Square-Duct flow, and later I will show some results and discuss the conclusions of the paper. Simulating turbulent flows via direct numerical simulations has been a problem for a long time because it's computationally prohibitive for most applications. An alternative to DNS, large eddy simulations, although cheaper, are still computationally costly. As a consequence, industry still has to resort to the popular yet physically poor Reynolds average Navier-Stokes, or RANS for short. RANS models simplify the flow's physics by a time averaging procedure, but this procedure, although greatly reducing the computational time required for simulations, greatly impairs the simulation's accuracy. So a promising compromise between the high fidelity simulations and the low cost of the RANS models is the use of machine learning techniques. The two main reasons for coupling machine learning and turbulent simulations are the increasing availability of data from high-fidelity sources like DNS, LES, and experimental, and the development and popularization of machine learning techniques applied to engineering problems. Most works that use machine learning techniques to correct RANS simulations did so by using the Reynolds stress tensor as the machine learning target. In these approaches, the predicted Reynolds stress was directly injected into the mean momentum balance, as shown here in equation 1, and therefore correcting the RANS mean flow. Here in table 1 I present some of the representations of the Reynolds stress or its divergence employed in recent literature for data-driven machine learning predictions and corrections of RANS flows. As can be seen here, most works try to directly represent the Reynolds stress and use it as a machine learning target. Some of them are unable to correct the mean velocities because the predictions weren't as good as expected, and the only exception is the work by Cruz and others, which does not directly aim at the Reynolds stress, but rather it uses its divergence as the machine learning target. So all of these works bring up the question, is it possible to use a transport equation for the Reynolds stress fueled by a source term that corrects both the velocity field and the Reynolds stress? We depart from the Reynolds stress transport equation as presented by Thompson and others. In this form, the equation combines all of the terms that require modeling in a single tensor named gamma. In theory, it would be possible to use gamma as the source term for the equation and then correct the RANS flow. But in this way, the numeric behavior of the solution was undesirable and no convergence was encountered. To ensure numerical stability and convergence of the model, two modifications were done. First, the production terms were incorporated to the source term gamma. Second, an additional turbulent viscosity was introduced into the diffusive term. This resulted in equation number 3, which is basically an advective term in the left-hand side, a diffusive term in the right-hand side with the increment of turbulent viscosity, and the source term gamma. With the modified Reynolds stress transfer equation, a data-driven turbulence model was constructed. This model coupled the Reynolds stress transfer equation, the mean momentum balance, and a pressure correction, forming a set of 10 coupled partial differential equations. The iterative process to correct the RANS simulations were organized in the following order. First, the machine learning predicted source term is provided by a suitable machine learning technique. Second, the Reynolds stress R is updated by equation 4, which is the Reynolds stress transfer equation presented earlier. Third, the mean velocity field is corrected by the deviatoric part of R through equation 6, which is the mean momentum balance. And lastly, the pressure field is updated and continuity is ensured through a pressure continuity correlation. The proposed data-driven turbulence model was evaluated in the Square-Duct flow. The Square-Duct flow is a classical example of an accuracy of very popular RANS models. These models rely on the business hypothesis to model the tensor B, which is the deviatoric part of the Reynolds stress tensor. They are unable to capture the duct's secondary motion, which occurs in the vicinity of the duct's wall, as can be checked here in the simple schematics in figure 1. To correct the baseline K-epsilon Square-Duct simulations, neural networks were trained to predict the source term gamma. The neural networks were trained using the DNS database by Pinelli and others, and this database contains 6 simulations with different Reynolds numbers. Here in Table 2, I present the neural network inputs. They are based on the tensors S, which is the mean strain rate tensor, P, which is the non-persistence of straining tensor, S squared, the Reynolds stress tensor, and the source term gamma. 4 out of the 6 DNS simulations of the Square-Duct were used for training. Another entire simulation was used for validation and another one for testing. It is based on the network's performance on the validation group that the training is interrupted, whereas the testing group is kept apart for evaluating the network. Neural networks can be summarized as a tool to establish a functional relationship between a set of inputs and outputs. In our case, the inputs are the RANS tensors and vectors from Table 2, and the outputs are the components of the gamma tensor from the DNS simulation. Here are presented the neural network's predictions. On the left we have components XX, YY, and ZZ of the gamma tensor, and on the right we have the XY, XZ, and YZ components of the gamma tensor. DNS fields are displayed for comparison alongside the predictions. As can be seen, there's barely any noticeable difference between predictions and the DNS fields. What draws more attention, in fact, is that the predictions are much smoother spatially than the DNS fields, as can be seen in some of the predictions, especially the XZ and XY, YY, ZZ, and YZ components in these highlighted areas. Now that we have the neural network's predictions, we can correct the RANS simulations. But before we present these results, we have to discuss some of the numerical configuration used in the simulations. The RANS, the DNS, and the corrected simulations all present the bulk velocity condition on the duct's cross-section. The bulk velocity in these simulations was of 0.48 meters per second. The initial conditions and boundary conditions of the corrections are presented in Table 3. The initial conditions for the velocity field is the RANS velocity, while no slip was imposed on the walls. For the Reynolds stress tensor, both the initial conditions and boundary conditions were the same, that is, the tensor was null, both at the wall and inside the duct. The pressure field had as initial conditions the RANS pressure, and zero gradient was imposed on the walls. The data-driven turbulence model was implemented in OpenFOAM 7, and the simple foam solver was used. The simple foam uses the simple algorithm to couple velocity and pressure. The turbulent viscosity required by the Reynolds stress transfer equation was taken from the baseline K-epsilon simulations. Since the duct presents symmetry in its center line, only one of its quadrants was simulated, and all corrections were performed on the Reynolds equals 2900. Here I presented the corrected Reynolds stress tensor after the injection of the predicted source term gamma. On the left we have the normal stresses, and on the right we have the shear stresses. For comparison, both RANS and DNS fields are also displayed. As can be seen, the corrected fields are much closer to the DNS fields than to the RANS. Once again, very few difference between the DNS and the corrected fields can be spotted at all. And the great agreement between DNS and corrected fields occurs both in terms of shape and magnitude of the components. These are the results for the corrected velocity field. Once again, the baseline RANS and the target DNS are displayed for comparison with the corrected fields. Here on the top row we have the main velocity component, and on the other two rows we have the secondary motion. Once again, there is a great agreement between corrected and DNS fields. The non-existent recirculation on the baseline RANS was efficiently corrected. It is possible to take a closer look at the velocity corrections if we analyze the velocity profiles of all three velocity components. On the top left plot we have the main velocity component. In red we have the corrected, in blue DNS, and in black RANS. It is readily noticeable that the corrected field is much closer to DNS than the baseline RANS. Here on the right you can see the y component of the velocity, and on the bottom you can see the z component of the velocity. On both of them you can notice how the corrections are much closer to DNS than the no RANS components. Here we can take a closer look at the corrections of the secondary motion in the duct and how close the corrections are to the DNS. Concluding the presentation, a data-driven turbulence model based on the Reynolds stress transfer equation was presented. And by using a DNS database and neural networks, the model successfully corrected the turbulent flow in the Square-Duct. Specifically, the non-existent recirculation on the baseline K-epsilon simulations was consistently recovered. This was the first effort in using machine learning predictions to correct not only the velocity field but the Reynolds stress tensor as well. The results demonstrated that the corrected turbulent stresses were much closer to DNS than the baseline RANS simulations. As a direct consequence of that, the mean velocity field was also much closer to the DNS target than the baseline RANS. Most importantly, this work's methodology made possible to achieve comparable to DNS accuracy, both in terms of turbulent stresses and mean velocity field, while still requiring simulation time of the same order of magnitude as simple RANS simulations. We would like to acknowledge the support provided by the CNPq and the Copy Institute of the Federal University of Rio de Janeiro. And these are the references cited during this presentation. I would like to thank you for your time, and I will be happy to answer any of your concerns in the comment section of the video.